Very welcome to our next session of the Fractal Geometry Seminar. And our next speaker is Alex Rutar from University of Jyväskylä, and he will talk about dimension classification and branching functions. So please.
Great. Yes, thank you. Yeah, it's great to be back. Yeah, so in this talk, I would like to talk about something which I'm going to call dimension classification. I don't think it's like formally written down like this anywhere, but the general idea that the general type of question that I'm interested in is the following. So let's suppose I'm given some sort of family of dimensions. I guess by dimension, I mean this really in a very broad sense. I mean like some sort of parametrized family of functions which take sets and output numbers. So what I'm interested in is, given this family of dimensions, I'm interested in this question. What is the set of functions which can appear? So for some family of sets E. So let me give some kind of classical exercise. So maybe I'm interested in things like the Hausdorff dimension, the packing dimension, the lower box dimension, upper box dimension, and I'm interested in their values where I range over all subsets of RD. So this is a pretty not too hard to show that these dimensions need to satisfy these following inequalities. That of course all of these need to be at least 0. The Hausdorff dimension is supposed the packing dimension, which is supposed the upper box dimension, and similarly for the lower box dimension, and then all of them are at most D. But on the other hand, given any 4 values which satisfy these inequalities, of course we can come up with some set which attains these as the values. So this is given the fact that we know that we have a general subset of RD, we can't say anything else. This is the most information we can say about these things. So the first, I guess, at least as far as I'm aware, kind of a non-trivial result about dimension classification applies to in the case of the intermediate dimensions. So I'm not going to talk about intermediate dimensions anymore, but I will at least mention them for those who are familiar. But the intermediate dimensions are some sort of family of dimensions which are continuously parameterized by some parameter theta. So in a paper with Amman Menaki from a few years ago, we solved the problem for the intermediate dimensions. So you have the usual monotonicity constraints, kind of similarly to the case for the Hausdorff and the dimension, there are some monotonicity constraints. But because this family of dimension is somehow defined in a way which is kind of has like this parameter theta, it turns out there are extra rules about what sort of functions can appear as intermediate dimensions. So there's an extra derivative constraint on top of just kind of the trivial monotonicity constraint. And then these two constraints there's like a finite set of rules which fully describe which functions can appear as the intermediate dimensions of some set. So what I would like to talk about in this talk is the Hausdorff spectrum on the lower spectrum. So these are also a notion of dimension spectrum, so they're defined, they're parameterized, they're defined for some value theta lying between 0 and 1. And the Hausdorff spectrum and the lower spectrum capture the sort of the worst case, the maximal branching of a set and the minimal branching of a set over all locations and between pairs of scales which are related by this parameter theta. So the Hausdorff spectrum is the smallest value of S, such that, well, if you I mean, this pointer doesn't work, especially people online can't see it. But anyway, the Hausdorff spectrum, if you look at the value here, it looks like the box dimension. It's just we're looking at the covering dimension, the covering number. Oh no, that's not good. Something's wrong. There we go. I can't. If I touch the screen, then it changes. That makes sense, right? Yeah. So if we just were interested in box dimension, then we would just ignore the ball here, and we just have 1 over r to the s. And the Hausdorff spectrum says, well, let's look at the worst case covering number except inside a ball of radius r to the theta, and we take the supremum over all x. And there's a constant here which is allowed to depend on s, but certainly not on r. And then to get the lower spectrum, we do the exact same thing. We just swap the inequalities. Instead of taking the infimum, we take a supremum, and instead of asking for an upper bound, we ask for a lower bound. So I think hopefully everyone's at least heard of the Hausdorff spectrum and the lower spectrum. But anyway, yeah. So some notation for this. Yeah, I'm going to write dim A with a superscript theta for the Hausdorff spectrum and dim L with the superscript theta for the lower spectrum. So for a given set E, we can think of this as a function of theta. So the question that I'm interested in is, what functions of theta can appear for subsets of RD? So if you give me a subset of RD, then this is some function of theta, which satisfies some rules, and I want to ask what are the rules it has to satisfy. And conversely, I would like to have this list of rules which says, if you give me a function which satisfies some set of rules, then I can give you a set for which that function is attained. So this is what I mean by classification of dimension. Okay, so at least it turns out that when you're writing down all of the inequalities that these things have to satisfy, it's a bit more natural to do some sort of normalization. So the normalization that I want to do is I want to multiply by 1 minus theta. So instead of thinking about the asymptotic spectrum as a function of theta, I want to think of 1 minus theta times the asymptotic spectrum as a function of theta. This is just to make the statements simpler to write. Yeah, so this was a paper that I wrote. Actually, I wrote this paper only a few months after the paper was online, but it wasn't published until 2 years later. Solves this question for the asymptotic spectrum. So what is it saying? It says that the set of functions which could appear as the asymptotic spectrum of some subset of Rd. Well, there are 3 rules that this function has to satisfy. Well, the first rule is that it has to be decreasing. The second rule is that it has to be d-Lipschitz. So this is sort of where the dependency on the dimension comes in. And then the third rule is that it has to satisfy this functional equation, which kind of looks like some sort of submultiplicativity in some sense. So I'll talk more about where these are coming from. But anyway, the point is that there is a very concrete answer here, and the concrete answer says that, look, so there's some set of inequalities that the function has to satisfy, and if you satisfy these inequalities, then you're necessarily the asymptotic spectrum of some set. And the first direction had been known for a while before, in the sense that it was known that every asymptotic spectrum function had to satisfy these 3 rules. So the interesting part of this paper was going the other way around, was starting with something which the function which satisfies these 3 rules to construct a set which has this as the asymptotic spectrum. Okay. So I want to talk a bit about the proof, and like I said, the non-trivial direction. Here's a quick sketch of what this function looks like, just so you have something in your head. So yeah, so this is the sketch of 1 minus theta times the asymptotic spectrum of theta. So well, it has to be a decreasing function, so the orange line has to be decreasing. It has to be d-Lipschitz, so it can't have slope, which is too large. At 0, we get just the upper box dimension at 0. At 1, this function always has to be 0 because we're multiplying by 1 minus theta. And this third equation, this equation that looked like kind of like submultiplicativity, you can reinterpret this equation as some sort of like inequality about slopes. That if I look at the 3 points with lambda, and theta, and I draw the line, the secant here, and I compare the slope to the secant from theta to 1, that the secant, the second slope has to be larger than the first slope, has to be steeper than the first slope. So this is what these inequalities mean. So it's not too important to understand precisely what these inequalities mean, but this is just some picture that you can have in your head for what these functions have to look like. So for example, any convex function is possible, for instance. That's easy to see. But there are lots of functions that are not convex that also satisfy the inequalities. Okay, so I want to say a bit about the proof. So like I said, the interesting direction of this of the paper, the interesting direction is I want to, given a function satisfying the constraints, I want to construct a set which has this as the asymptotic spectrum. So the construction that I use for the set is I think quite natural. And here's the construction which is sufficient for the set. So let's fix an increasing d-Lipschitz function which takes values 0 and 0. And let's just suppose it takes integers to integers. I mean, you can change the function up to a small. You can just make a small change and you can guarantee that it maps from integers to integers. That's not a problem. And then now I'm going to define some sequence. Well, it's an integer value function which is d-Lipschitz. So if I look at the differences, well, the differences certainly have to take values between 0 and d. Now I'm going to use these differences to inductively construct some sort of some set. So I'm going to inductively construct a family of dyadic cubes. I'm going to start with the dyadic cube, which is just the unit square. And then at step k, if I have some family of cubes, let's say q sub k minus 1, and I have some q, well, I'm going to replace that cube with 2 to the a sub k cubes at the next level. And I'm going to do this with every single cube in the exact same way. So I'm going to always replace each cube. So the point is that across the level, the number of cubes what I do is the same. So at a given stage, I always replace by the same number of cubes, but the number of cubes that a subcubes are replaced by could change at each level. And then I'm going to define the set like this. Call it k sub f, because f is sort of the thing which is governing this construction, and it's just sort of the nest intersection of this family of cubes. Okay, so hopefully everyone has seen something like this, but again, I prepared a picture. Guess why not? Okay, so we start with the unit square in this case, and then now if a1 is 1, it means we subdivide to a one-dimensional subset, like one dimension like this. The number is like one-dimensional, so we subdivide to 2. If a2 is 2, then I subdivide each of these squares down to 4, because 2 to the 2 is 4 subpieces. And I do this again. Now again, A3 is 0, so that means I replace by a 0-dimensional subset, which is a single square. I replace every single square with a single square, and then I replace every single square with, say, 2 squares. So the point is that, I mean, the position doesn't matter. The position is totally irrelevant. The main point is that you do the same thing in every single square, but you do different things between different levels. So this is a relatively restricted family of sets. I mean, it's much smaller than the class of general sets, depending on what you're doing. And this is the construction. Cool. Okay. Yeah, so this set, case of F, I mean, there's like people have been studying variants of the set. I mean, at least I like to call them uniformly branching sets. I think this is reasonable. So kind of the convenient feature of this construction is that the asymptotic spectrum of the set is very concrete. We can just write down the asymptotic spectrum kind of in terms of this function. This is the simple computation because the set looks the same everywhere. Sort of there's no dependence on the point. So the only dependence that shows up is on the scale, but all of the information about the dimensions as a function of scale is encoded by this d-Lipschitz function f. So the asymptotic spectrum looks like this. So basically the idea of the construction is to choose the function such that, oh wait, so what do we want? So we've prescribed this function on the left-hand side here. So we want this value 1 minus theta times the asymptotic spectrum of case of f. We want that to be some function, I call it bar phi. So we can just choose the function f such that this is literally an equality for infinite many k's, and then we just need to be careful that we don't interfere with the construction at other scales. So otherwise, maybe one possible way is to make it constant, which is like 0-dimensional or no branching. I mean, there's lots of computations to do that you have to check that this actually works, but like morally this works. Okay. Yeah, so I just wanted to say, so f is called the branching function of case of f. Yeah, so I don't know the full history. I mean, Tomasz is actually the better person to ask the history. At least the first time I heard about this was in a paper written by you and Pablo, where you're interested in general sets. So this is somehow, the idea to study branching functions goes back to this idea of Bourgain, where, like, given a general set, you can always pigeonhole a subset, which is uniform in a meaningful sense. And then they were interested in the distance set conjecture, and sort of like, it turns out that if you can solve the distance set conjecture for some special families of sets, then you can say something interesting about like all sets, kind of by using branching functions and saying some combinatorial facts about Lipschitz functions. So anyway, so this is like sort of like, and it turns out that branching functions, at least in general geometric measure theory, I mean, are very important. There's like tons of, like a lot of questions can be reduced to some sort of study of branching functions, or saying something meaningful about branching functions is very important. But I'm not going to go too much into that. I just want to say that like the idea of doing this and like the idea of thinking about branching functions is very important, and I won't talk any more about that. But if you're interested, you can talk to me about that after. I can say what little I do know. So anyway, so the point here is that I'm going to say is that for this construction, in order to get this classification for the asymptotic spectrum, we actually didn't need to consider all subsets. We only needed to consider uniformly branching sets. That was enough. Okay, that's just what I'm saying here. Yeah, so all possible behavior of the asymptotic spectrum is realized by a uniformly branching set. So it turns out this is also the case for the intermediate dimensions. So I mentioned the intermediate dimensions earlier. I didn't say what they were. I didn't say anything else. But there's like an analogous problem that you can ask for this other notion of dimension called intermediate dimensions. And it's also the case for those sets that you only need to consider uniformly branching sets. That there's some set of inequalities that are satisfied for all sets. But in order to kind of realize a function with those inequalities, we only need to consider the restricted factor of uniformly branching sets. Okay. So then the natural question is, what about the lower spectrum? Right? So, I mean, at least like when I first heard about this problem, or when I first started thinking of the problem, my first instinct was like, well, surely it's the same as the asymptotic spectrum, right? You know, it's like you just swap all the inequalities, everything should be the same. So it actually turns out this is not the case. So basically the problem is that infimum is really unstable. This is essentially the issue. So let me give an example. Okay, so let's take the set. This is a very trivial example, right? But I think it kind of captures the spirit of what's going on. So if I look at the covering number of a ball of radius 1, well, of course, any ball of radius 1 centered in the set E has to contain an interval 1/2, 0, 1/2. So no matter what the little value of little r is, it has to look like 1/r. But if I change the upper scale by like a small amount, let's say by a factor of 2, then suddenly the infimum jumps down to 1.
Sorry, it should be the opposite, right? The first should be 1/2, and the second should be 1.
What?
So the opposite, not the neighborhood of 1, is needed to be covered with around 1/r many balls, and not.
No. Sorry, x is the center. X is the center.
Oh, x is...
One is the radius.
Oh, yeah.
Sorry. Yeah. So x, exactly. It's an infimum over all x. Yeah. Because when the radius is too big, you sort of can't see the fact that there's a single point. This is like underneath the resolution. But then once the radius drops just enough to, like, the thing that matters here is the gap size, right? Like the spacing between one and the other interval is 1.5. But of course, this is like a super trivial example, right? There's nothing sort of like substantial going on here. But you can imagine like variants of this happening at like infinitely many scales. So that somehow like to understand the lower spectrum, it sort of like matters like how the pieces of your set are spaced relative to each other. And the covering number can jump in this very arbitrary way. In the sense that like, you just change the radius by, you change the upper scale by a tiny bit, and it can cause the size to jump by this large factor. Yeah, and this type of behavior is impossible for uniformly branching sets. So you can just think about this a bit, that if you have a uniformly branching set, and you change either of the radii by some small amount, the covering number can only change by like a corresponding d-dimension, kind of like a d-dimensional factor at most. So what this means is that if we want to understand like all the possible behavior in the lower spectrum, like at least in principle, we are going to have to construct sets which are not uniformly branching in order to understand something. So this is like, so it's genuinely different. So it's genuinely more different. Yeah. So I just say this, but yeah, so the proof technique for the XY spectrum in intermediate dimensions, it does not work. So it's not going to give us all of the possible functions. Okay, so we need to say something more general. So what I want to talk about is, I want to talk about a variant of sort of like this one-dimensional branching function, which I'm going to call two-scale branching functions. So this, so here's the first variant. This is in this paper with Vilma that I think Vilma talked about a month or two ago, sometime recently. So the idea of this, the idea of a branching function, this two-scale branching function, is instead of thinking about a dimension, instead of thinking about some sort of like statistic defined in terms of covering numbers, let's just think about this function which itself describes the covering numbers kind of as a function of scale. So we're interested in sort of the dimension, but like as an explicit function of scale. So here I define this function beta, which has this particular normalization because it makes the algebra nice, where I just define it to be the covering number of some ball. The supreme over covering numbers of ball, where the lower scale is 2 to the minus u and the upper scale is 2 to the minus v. And I emphasize here that in this case, this is not for the lower spectrum, this is for the XY spectrum, but it's a supreme over possible scales. Okay. So this function has some properties. So, I mean, some are very easy to see. So it's very easy to see that it's increasing in u and decreasing in v, just as much as the covering number. It's like slightly more difficult, but it's still easy to see that this has to be a d-Lipschitz function. So this is somehow why one would choose the normalization to be like this. I mean, I'm cheating a bit. It's not literally d-Lipschitz. It's like kind of d-Lipschitz with some sort of like error term, but the error term can be controlled. So these are natural. So these are natural if you think about the one-dimensional branching function. These are both very reasonable conditions. And then the point is, when you have two scales, you have one extra condition, which you do not have for this one-dimensional thing, which is that you have subadditivity. That if I have three different scales, let's say 2 to the minus v at the top, then 2 to the minus w in the middle, and then 2 to the minus u at the bottom, well, then the covering number from the top scale to the bottom scale is rounded about by the covering number from the top scale to the middle scale multiplied by the middle scale to the bottom scale. And I take a log, right? Because you can just build this manually. You know, if you want to cover a ball at some small scale, well, you can first cover it in an intermediate scale, and then take each ball in that intermediate cover and cover it at a small scale. And you multiply things together. We're taking a supremum, which means that all the inequalities go the correct way.
So you assume that U, W, V are in that order, right?
Yes, exactly. Yeah. U, W, and V are in this order. Yeah, sorry, I should have written that down. I realized I didn't. Yeah. U is the largest, W is in the middle, V is the smallest. I think I didn't write this any times, so you're gonna see this more, and it's always the same. Yeah. Okay, yeah, so this is basically one of the things that we proved in this paper. I mean, we were interested in homogeneous. We were interested in some other things, but kind of along the way, this is something that we proved, which is that on one hand, if I have a subset of RD, well, then there exists some function which is literally d-Lipschitz, which this thing coincides with up to some sort of error. And conversely, if you were given a function which satisfies the EC rule, which is like d-Lipschitz satisfies the subadditivity inequality, satisfies this monotonicity inequality, then you can find a subset of RD which has this as this function. In other words, these are the only three rules. But if you're kind of willing to blur your eyes up to error of some sort of fixed additive error term, these are the only three things that you can say. Yeah, every function looks like this. Yeah, so one particular kind of consequence that we also noted in that paper was that this does imply the classification of Asphalt spectra. So we can read the Asphalt spectrum off of this function in the following sense. That 1 minus theta times the Asphalt spectrum is just the limit supremum along, because let's remember what the scales are like. When we take the scale the value u corresponds to scale 2 to the minus u. So the value theta times u corresponds to scale 2 to the minus theta u, which is 2 to the minus u raised to the power theta. So this is sort of like the correct spacing of the scales. So the exponentiation turns into multiplication. Then we have to normalize by u because we're dividing by. So the Asphalt spectrum is like, we have this function which is defined on this kind of this like triangle, right? We have this like triangle here, which is a set of all ordered pairs. And the Asphalt spectrum is like, take the limit supremum of this two-scale branching function along a diagonal line with slope theta. So in particular, using this, you can just like, you can kind of get an alternative proof of the classification of Asphalt spectrum, which I'll briefly explain. Next slide. Yeah. Okay. So what I've written down here is I've written a little table. So on the right-hand side, we have the two-scale branching function. And on the left-hand side, we have the corresponding like 1 minus theta times the Asphalt spectrum, which is obtained in this way by this limit supremum procedure. So first of all, this function beta is decreasing in the second parameter. So when you take this lim sup, of course, this implies that the var phi is decreasing. Easy to check. So the function beta is D-Lipschitz in both variables. So in particular, var phi is some sort of limit supremum of D-Lipschitz functions. Well, it certainly has to be D-Lipschitz as well. And then this is where this third inequality is coming from. So now we can kind of have some reasonable. Oh no, again. We can have some reasonable justification for the third inequality. That subadditivity for the function beta, if you sort of like normalize and you take a lim sup and you kind of unwind all the extra factors of theta, you precisely get this submultiplicativity type inequality. So this inequality is just subadditivity of covering numbers and nothing else. And the very, very bottom, what I've done is I've written down sort of like how, if you have a function var phi, how you can obtain that function from some function beta. So if I have some function var phi satisfying these three inequalities, I can just define beta in this way. And it's very easy to check that these inequalities exactly translate to show that beta satisfies these three things. So this is how you could, another way to prove the classifications for the Asphalt spectrum is starting with a function var phi, define a function beta in this way, and then use this more general constructor technique. This theorem from 2 slides ago that I mentioned, that all of the functions beta which satisfies these three rules, there exists some subset which has this as the branching function. Okay. So in that paper, like I said, the Asphalt spectrum result had already been proven. So sort of like that wasn't new, but at least it gave some new proof. But the point is that actually we can use this to study the lower spectrum as well. So we can ask the same question for the lower spectrum. So for the lower spectrum, we're also interested in the same thing. So I think this is maybe more natural than the lower spectrum, is this function, where instead of taking a supremum, we take an infimum. Here I've written this like some sort of like packing. So this is just some technical detail. You can just write the cover number if you really want to. It just makes some things slightly nicer. But it's the same up to a constant, so it doesn't matter. Yeah. So I define this function is analogous to the branching function, this kind of upper version, except now instead of taking a supremum over scale, I take an infimum over so supremum over location, I take an infimum over location. Okay, so again, it has some properties. So first of all, of course, like instead of a supremum, I'm taking infimum. So this sort of instead of having subadditivity of covering number, we have superadditivity of covering number. So this is basically the reason for choosing this 4 times 2 to the minus u separated packing, is that it makes this literally true. If you just use like covering numbers, this would only be true up to a constant or something like this, up to add error term. So that's true. And the second thing is that, well, this is a D-Lipschitz function, but the thing is it's not D-Lipschitz in both variables. It's only D-Lipschitz in the first variable. So when you fix the upper scale, it's D-Lipschitz as a function of the lower scale for fixed upper scale. So I just want to recall this example. This is the exact same example before. So we take 0, 1/2 with 1. Well, if I plug in the value 0, then the upper scale has radius 1. Then of course I have to capture the 0, 1/2. But then the moment I make it 1, then suddenly I will only see the single point, and then it drops down to 0. So like this is like definitely not a Lipschitz function as a function of the second variable. So that means that this constraint here, this fact that it's D-Lipschitz in U, and not in V, there's literally nothing you can say. This is like the max size possible jump. There's truly nothing you can say about the second variable. Yeah, so I say non-Lipschitz. Okay, So what I've done here is I've written down the three properties of theta, of the upper, the branching function defined as the supremum. On the left, I define the one with the defined intercept in the theorem. So again, we have this increasing in u and decreasing in v. So this property is still satisfied for the lower version. But for the lower version, it's actually now formally implied by superadditivity. You can just check, because these numbers are always 0. So in particular, you get this increasing kind of as a consequence of one of the other inequalities. So yeah, so we have an upper bound, so we have subadditivity replaced by superadditivity. And then instead of having a de-Lipschitz property in both variables, now we only have a de-Lipschitz property in the first variable. So these are the differences between the upper and the lower. So far, so good. Okay. Yeah, so this is something that we can do. So we can prove an analogous result from the paper with Vilma. So we can, this is joint work with, it's very recent. I think this is on arXiv last week. So what does it say? It says if I have a subset of RD, well, then I can find a function satisfying these inequalities, which is like the same. Well, now we're no longer up to a fixed additive factor because if you're comparing Lipschitz functions, like it's very easy to say that two Lipschitz functions are the same. Whereas here, because I'm comparing like functions which are not even continuous, I basically want to allow myself to change the bottom value of it by some fixed amount. So you can think of this as saying like these are the same up to some constant error term, up to some like additive constant. So anyways, if you're given a subset of RD, then the function, the kind of the corresponding infemal branching function or the corresponding lower branching function has to satisfy those inequalities. And conversely, if you have a function which satisfies these inequalities, then there exists a set, which has this as the one. So the construction here is like you have to be slightly more careful than you have to be for the other version, but yeah, so there's some differences, which I'll talk about at the end, which I think I will have time. So I'll talk about that later. Okay, so of course we can also do the same thing as for the axial spectrum. The lower spectrum is also realized in this way. That the lower spectrum is realized as this limited theorem of the same thing. We look at the line with slope theta, and instead of taking the lim sup of the upper branching function, we take the lim of the lower branching in the exact same way. So it's the same. Yeah, so remember this also resolves the classification for the lower spectrum using the exact same construction. Well, given a function of R5, we define gamma to be like u times gamma of v over u. Or something like this. Okay. So what are the corresponding properties that this thing has to have? So on the right here, I've written down, again, the axial spectrum. This is 1 minus theta times the axial spectrum. So what were the three conditions that we had? Well, we had this decreasing property. We had this kind of secant property or submultiplicativity kind of property. And then we had a de-Lipschitz property. So these are the three things that the axial spectrum has to satisfy. So these are the corresponding properties that the lower spectrum has to satisfy. Well, first of all, it has to be decreasing. But as we saw for the general function, that the decreasing property is actually just formally implied by this kind of super multiplicativity, this like secant type property. But now, instead of a de-Lipschitz property, we get something else, which looks like, which is like a secant. Again, some sort of like slope condition. It's implied by being de-Lipschitz, but it's strictly weaker. So where is this inequality coming from? So this inequality is coming from the horizontal de-Lipschitz property. So that even though if you were vertically de-Lipschitz, then this function would have to be de-Lipschitz because as you vary theta, you're sort of like moving up. But if you're horizontally de-Lipschitz, you can still say something non-trivial, or you can still say something in the sense that. So remember that the lower spectrum is defined as a limit infimum along the line with slope theta. So let's say this function at value theta, well, it's realized somewhere. Let's call it the place where it's realized. It's called that u. So it's realized it's realized at u at time for theta, right? So what I'm interested in doing is I'm interested in an upper bound on this like function of R5 at the value of lambda theta. So I draw the line with slope lambda theta, and then I know that the value here is small, and I know that it's de-Lipschitz horizontally. So of course I can just apply the de-Lipschitz property. So if I know the value here and I know it's de-Lipschitz in this direction, then I can get an upper bound for the value here. So and this gives an upper bound for this. And you just sort of have to unwind exactly what this means. So it turns out that being horizontally de-Lipschitz still provides you some sort of inequality. This inequality, for example, is enough to prove that it's continuous, but it's no longer going to be Lipschitz in general. Okay, yeah, so here's a quick plot of this again. So again, the orange line is 1 minus theta times the lower spectrum. So we have this, the secant condition is of course the same. So if we draw the secant from lambda theta to lambda and then from theta to 1, that the first slope, now that the inequality reverses, so it has to become flatter. And then the first condition, instead of saying that it has to be Lipschitz, the first condition says, if I look at a value lambda, and I draw the line which connects the value of the graph of the value lambda to the value 0, comma d, that the graph to the left of it has to lie underneath this for all lambda. So that's what that first condition is saying. So it's like a weak convexity only at the endpoint, or something like this. But of course, the smaller the value is, and the closer you are to 1, the worse the farther away from being d-Lipschitz this gets. Right? Whereas if you were d-Lipschitz, then that would be the same as saying that you draw the line with slope d coming off of there, which is of course much weaker. Or much stronger. This is much weaker.
And it doesn't even need to be continuous, right?
So it does have to be continuous because if you combine these two inequalities, it does force it to be continuous, but it requires technique. Yeah, so it does have to be continuous. Yeah, but so like one for example, like whereas for the asymptote spectrum or like this 1 minus theta asymptote spectrum, you can get any concave function, basically, like any decreasing concave function, whereas now you can get any decreasing convex function. So that's the kind of like, but of course there are like this function drawn here, for example, there are more functions than just the decreasing convex constant. Okay, and then yeah, so then this kind of gets this result now follows. Yeah. The lower spectrum, the classification looks like this. That we have these same inequalities that I mentioned before. We have this super additivity, or sorry, this super multiplicativity property, and then we have this kind of replacement property for d-Lipschitz, which is the second inequality. And then these are the only two things you need. Yeah, so I say here, I emphasize that if I started with a uniform set, then this second inequality is replaced by d-Lipschitz. So if instead of asking for this like ranging over all subset of RD, I only asked ranging over like uniformly branching subsets of RD, then you would get a family function which is strictly smaller. You would get the family functions where you replace the second inequality with d-Lipschitz functions. So
is alpha's regular enough to uniform?
So alpha's regular makes this a constant function.
Oh, yeah.
Even stronger.
Yes,
Yeah, so uniformity is basically uniformly branching. That's the difference.
Yes.
Okay, yeah, so actually, because I have some time, I'm going to come back to this. So I'm going to come back to this, and I'm going to talk a tiny bit about this construction. So here's what do I want to do here? So I want to give a sketch of the construction of the set. So what's happening here? So here I'm given a function f. So it's a bit truncated, but I'm given a function f, which is which satisfies these inequalities for this lower two-scale bracket function. So it satisfies these two things. Well, the first thing is it's increasing. It's d-Lipschitz in variable u, and the second thing is it satisfies the super additivity. So these are just the conditions that we want. So what we want to do is we want to build a set which has this as the function. So if I fix some natural number, or like the natural number or 0, I can look at the horizontal strip. I can look at this function f sub k of u, which is kind of like the value of this function along the horizontal strip. So this first condition precisely says that this is an increasing d-Lipschitz function of u. So this is just a regular branching function. So this is like a regular branching function. So because it's a regular branching function, I can use the construction that I defined in the like talked about earlier to build a uniformly branching set, E sub k. And because I started with the value k, like the value k kind of corresponds to the top scale, which is like 2 to the minus k. So that means that actually the set is going to be quite small. So this set is going to live inside the interval 0, 2 to the minus k. So it's a uniform set with exactly with this branching function. And now I'm just going to arrange these sets in some sort of geometric sequence. I have to be a bit careful, so I'm just going to arrange a set E0, then E1, and then E2, and I'm going to space them in such a way that the spacing between the adjacent pieces is exactly 2 to the minus k, or like 2 to the minus k up to a constant, say. Okay, so on one hand, so what do we want to do? So we want to prove that the infimum over covering numbers, infimum over all locations of the covering number at scale 2 to the minus, of the top scale 2 to the minus k, the bottom scale 2 to the minus u, we want to show that that's given by the function f. So to get an upper bound for an infimum, we just find a single location. Well, the spacing is 2 to the minus k, so of course you can just like take like the left endpoint, right? If you just take the left endpoint of this interval, then the ball of radius 2 to the minus k intersected with e, well, you only see this at E sub k. And then E sub k was chosen to be a uniformly branching set. So the function, so gamma sub e, which is defined as an infimum, well, it's upper bounded by the corresponding dimension of the uniformly branching set at scale u. And this is just by definition f of u comma k. This is just how I define f. So basically, the spacing is kind of set up so that this just works exactly. Okay, yeah. So this is the thing. So the more interesting inequality I think is the lower bound, because for the lower bound now we need to say something about an infimum over all scale. So we need to guarantee that if you pick another ball at a different location, that we don't get something which is much smaller, right? Because this is the enemy. So first, there's two cases. So we have to consider an arbitrary value x. So k is some number which is potentially very large. So the first case is that x lands in some interval which is like much. So the interval e sub j is much larger than the scale 2 to the minus k, right? So imagine like 2 to the minus k. Imagine k is like 3 or 4. Imagine k is like 100, right? Then e sub k kind of lands somewhere over there. Whereas of course I could consider a small ball of radius 2 to the minus k inside e0. This is certainly something you have to be careful of. Okay, so what you want to do is, well, we want to compute 2 to the minus. We want to compute this covering number of 2 to the minus u at scale 2 to the minus u of the set E of this ball of radius 2 to the minus k intersected with E. Well, that's just the covering number intersected with EJ, because remember that the spacing of the sets was like order of size 2 to the minus j. So in particular, if we're smaller than k, then we can only contain, then we must be basically contained inside one of these things. So this is essentially equal to essentially being essentially exactly 1. And now the fact that E sub j is a uniform set, well, a uniform set, we can say something about this number. So for a uniform set, it doesn't matter what the value of x is. The only thing that we care about is the ratio of the covering numbers at scale u, scale 2 to the minus u, and scale 2 to the minus k. So because it's a uniform set, this is just this number. This is just exactly what it is, what it means to be uniform. Then we apply the definition, right? So this is just the definition. This is how we define f. But then now the point is that these horizontal slices are not just, they're not just like arbitrary Lipschitz functions. They're Lipschitz functions which are all constructed from the same original function type. And the original function has the superadditivity property. So we can use the superadditivity property to get a lower bound for this number. So superadditivity morally is saying that if we look at kind of like a small scale piece of something bigger, that actually we can't get anything. This is exactly what superadditivity is saying. Yeah, so here we get this precisely 2 to the minus u. Yeah, so this gives you the lower bound for value x in E sub j, where j is much smaller than k, where the kind of corresponding interval is much bigger. But this is basically the only case, because the size of the intervals are decreasing geometrically fast, which means that once I hit E sub k, all of the remaining pieces, the size is approximately the same size, right? The diameter of the kth interval versus the diameter of all of the remaining intervals combined. This is basically the same, because they're arranged with this like decreasing sequence of gaps and decreasing sequence of sizes. So morally, E sub k is contained in a ball of radius 2 to the minus k. If x is not of this order. I mean, it's not literally true. You have to kind of fudge the endpoints a tiny bit, but that's okay. Everything is up to a constant amount. So, and we already know that this works for E sub k because we chose E sub k for it to have the correct value. So basically, the only place our superadditivity comes in is to control the covering numbers of these balls, whatever it is, some small piece. So, I mean, it makes sense that we had very little to work with in the first place, right? Like we go back to the assumptions. I mean, these were the only 2 assumptions we had, right? Well, we use the first assumption to construct these uniform sets, and then we have to use the second assumption, but like surely nothing else. Then we use it exactly once, and that was exactly here to construct. All right, yeah. So that's a quick sketch of the construction for the subset gamma. Okay, so now to conclude, I want to mention 4 problems. So I think this is motivated by something Ishvan said. Ishvan told me I think Ishvan said something like aren't all the problems like about dimension classification solved? So my answer is no. So here are some questions that someone wants to solve. Someone wants to do something fun. Okay, so the first question that I want to ask is this question of called joint classification. So of course, like you could just fix the lower spectrum, or you could just fix the asymptotic spectrum. But it's also reasonable you could ask for functions which are realized simultaneously as the lower spectrum and the extra spectrum at the same time. So this just isn't just like the set of all pairs of functions, because for a fixed set, if you know something about the asymptotic spectrum, that actually gives you more information about the lower spectrum, and vice versa. If you know something about the lower spectrum, you get more information about the asymptotic spectrum. If you look at our paper, there's like a precise conjunction which is written down for what might be true. That's the first question. So the second question is for the modified lower spectrum. So the modified lower spectrum. So yeah, so calling the lower spectrum a dimension is like pretty borderline, I think, for a lot of reasons. Probably the reason that makes it the most borderline is that it's not even monotone, right? That if you like add more points, the lower spectrum can either go down or go up. at will. So the modified lower spectrum says, well, let's always force it so that it goes up. So that if you have so there's like increases. And if E is contained in F, then the modified lower spectrum of E is contained in the modified lower is bounded above by the modified lower spectrum of F. And to do that, we just monotonize the lower spectrum. We define the modified lower spectrum to take the supremum over all lower spectra of subsets. And then we can ask the analogous question for the modified lower spectrum. So for this set, the proof no longer works. So this construction that I mentioned before is just it doesn't work anymore. I think this is don't know how to do this. The third question, just to give it a question of another type of flavor, is for product sets. So if I have, so this question is kind of motivated by the following. So, okay, if you think about upper box dimension, if I know the upper, if I like I set E and I set F, and I know the upper box dimension of E and the upper box dimension of F, then of course the upper box dimension of the product has to be at least the maximum of the two, and at most the sum. But if you give any value in between, you can construct sets. So if you give any triple which satisfies these inequalities, then you can construct a set which satisfies these two things. So this question is asking, well, suppose you knew the Hausdorff spectrum of the projection onto the two values. Can you say something about the Hausdorff spectrum of the product? Like what information do you get about the Hausdorff spectrum of the product given the Hausdorff spectrum of the pieces? So I think there's something interesting thing to say. My guess is that there's going to be the usual monotonicity constraint, and there's also going to be some sort of like derivative constraint. Like the derivative of the function on here has to somehow interact with the derivative of the functions there. So there will be some extra condition like this, which requires some thought. And then the fourth question is very underspecified, and I think is easily the hardest question here. Is that there are like more general branching functions which you can define. So you can define like branching functions in point line space, for example. So there's this paper called Lower Bounds of Incidences by Alex Cohen and Cosmin Bogata and Dmitry Zakharov, where they're introduced this Heilbronn-Traub problem. And sort of what they do is they reduce some sort of incidence geometry problem to a question about branching functions, but they don't consider usual branching functions. They consider branching functions of like points and lines simultaneously. And these functions satisfy some like very difficult to prove inequalities. I mean, there's like the kind of the usual things like an analog of submodularity and like submodularity. But then they have these extra properties, which, for example, are consequences of the Furstenberg set conjecture, or the Furstenberg set theorem. So this question, to understand question 4, is like at least as hard as the Furstenberg set theorem, and potentially, and certainly harder. And the question is like, what are all the possible properties that branching functions of the point line space have? All right, and then to conclude, I will just put up this little slide, which has all of the properties, and I'll stop there.
Thank you very much. Questions, comments? Certainly have. What about the modified Hausdorff spectrum?
Oh, same. It's already done.
It's also, yeah. And also the intermediate dimensions.
Yeah, already done. Yeah. It's only for the lower spectrum that this matters. Yeah, maybe I can say something about that. So this construction just literally doesn't work because, of course, E0 is a subset. So I just discard everything else. I already get something which is bigger. So if I want to specify, the modified lower spectrum, then so there's no chance that this construction works for the modified lower spectrum. Something which does work, if you started with a uniformly branching set, then the modified lower spectrum and the lower spectrum are the same. So anything that you can get for a uniformly branching set will work. So for example, this says that there are lots of functions which appear as modified lower spectrum, but I don't know, actually, I can't even give you a function which has like some modified lower spectrum given, which is not Dirichlet's. Already this is something which I don't know how to answer. Yes.
Thank you. Further questions, comments, maybe people of the online world?
Yeah, I have a question. I'm not sure it makes sense. So Amla made made a further generalization of this spectrum to allow the stuff. So does it make sense to ask similar question concerning that? I'm not sure that my question makes sense.
Yeah, so we answered something like, so there is a question like this. So I think the natural question like this is, suppose that you have an arbitrary, so what I don't answer this point. Suppose I have an arbitrary set, which has this like generalized Aswad spectrum for some arbitrary bounding functions. So the question is, can you come up with a uniformly branching set which has the same dimension for all of those functions? Yeah. And we were able to prove it for a countable family. So if you have a countable family of functions, then the answer is yes. But we weren't able to answer the question in general. Yeah. So
So if there are no further questions, then let us thank Alex again.